Hi guys, as promised, I'm going to go through a few of my slides that I think arguably cover the most important content in this class thus far and really are going to allow us to set up a foundation to complete the rest of the course. Everything we've been doing is really building that toolbox that Dr. Axelson might have mentioned to just kind of understand where all this content's going to come into play and how it's really going to come all together near the second half of the class. So I did include a slide from 2 weeks ago. I think a conjugated system, the understanding what that really is the fundamental idea of this class overall. It's going to allow us to understand how these electrons flow through the molecule and how that affects reactivity between another molecule in itself. So as we know, a conjugated system is composed of 3 or more p orbitals, and all those p orbitals have to be adjacent to each other, so they properly overlap. I always think of this as those adjacent p orbitals kind of forming a tunnel that our electrons can travel through. I'm a big analogy user. I think that just helps so much with this content especially. I always think of this kind of like, let's say I have this molecule here, just something simple. And if I have my p orbitals, I'll represent that as little shapes that we know our p orbitals are. If I was in person, I'd kind of show you guys that, well, this p orbital system, right now the way we have it drawn is very discrete. We don't really get like that moving image of what's going on in real life. So I always kind of go and like pretend I have an electron. It's going to kind of be flowing through this whole thing very rapidly. It's a tunnel basically, as I said before. So even though we have these static images like this here, an electron, if I have like a single electron again, that thing is going to see all these p orbitals aligned and adjacent to each other and just flow through this as freely as it possibly can. That's going to lower that reactivity of our molecule, just lower the energy of it, I should say, and just give us a very stable molecule overall. This last point here, the p orbitals must be aligned. This is something that we won't talk about often. The only example that she will include if she does want to like throw that onto exam or something would be the molecule that looks like this, cyclooctatetraene. This is going to not be conjugated, even though we have p orbitals around this entire thing. Those p orbitals are not going to be aligned with each other just because this molecule in real life is bent. If we kind of looked down from this way, you kind of see that it would have that saddle shape that I'm sure she's mentioned before. But again, that's not much of an important thing. The main two takeaways from what a conjugate system should be are, of course, those first two. And then the aligned idea comes into play whether it's like px, py, or pz, because we know we have those 3 types of p orbitals available to us. But continuing on with the conjugated system, this, I think, is one of the most important things to kind of take away from the actual conjugated system idea itself. I know I'm going to say that about everything right now. Everything's important, but I'm trying to condense this onto a few slides because I know the lecture slides can get a little complicated. I've been there before, so I understand. But everything in my slides, I kind of condensed down from Axelson's slides and my own understanding of the content and what I did on my own to kind of make it more digestible. So everything with electron delocalization in terms of conjugation and resonance that we've talked about kind of comes into these 3 options we have. So we know that if we have a lone pair in an sp3 orbital, I know I have little pictures on the side, but I'm going to redraw some stuff here. Let's say I have this. I know that this is an sp3 hybridized carbon just because I have 4 things around it. And again, we have that implied hydrogen coming off somewhere right here. But overall, we have 2 carbons, that hydrogen, and then this lone pair, counting as 4 things. So we know that's sp3 hybridized. But the thing is that right now I can look at my carbon that my lone pair is on and kind of zoom out for a second. I'm going to go to my left, my right, and generally all around this molecule and see what other hybridized carbons or atoms I have surrounding my one with the lone pair. So here we have another sp3 hybridized carbon. There's also an implied hydrogen coming off of this here. So that's sp3 here. We also have another sp3 on this side. That's also going to be an sp3 hybridized carbon. We have 4 things coming off of that one there. And then my H atom, that's going to be a simple s orbital. We could just consider it as s, I guess. Same thing as sp3, just something that doesn't contain a lone p orbital. It's a very simple, just s orbital right here. So because I don't have any surrounding atoms that contain a lone p orbital, I know that this lone pair in the center here is going to be trapped. Like I was saying before, went a little too far. We don't have that tunnel, that conjugated system tunnel for these electrons to travel through. So here, this electron pair is not going to have any path to get through. It's going to be kind of stuck in this spot in the center right there. So we'd consider that trapped in an sp3 orbital. We can also have an orbital or a lone pair trapped in an sp2 orbital. And that would be a case where you see the lone pair on an atom directly connected to a pi bond. So if I look at this example here, I think this might be the best possible example in this case, but if I have my lone pair right here and I know that it's on an sp2 hybridized nitrogen, just because I have 3 things coming off of this nitrogen, I think to myself, well, when I say sp3 or sp2, or I meant to write sp2. When I say sp3 or sp2, I always think of that as my abbreviation for what I really have, which is 4 atomic orbitals coming off of my atom overall. So I'm saying that this nitrogen is sp2, but really what I have is 3 sp2 hybridized orbitals, and then my last thing would be that one leftover p orbital. So now I can delegate what all these bonds and lone pairs, like where they are in terms of which orbital they're filling out of these 4 atomic orbitals. And I know that any sigma bond like this, kind of like I said before up here, any sigma bond like this is going to be taken up by one of my hybridized orbitals. So a sigma bond here and here, those will be formed by my sp2 hybridized orbitals coming off of nitrogen. So I've got those taken care of, like that. And then we have to kind of stop and think for a second, because now our remaining things, I guess you can say, around this nitrogen are our lone pair and this bond right here. And that bond is going to be our pi bond. Any double bond is composed of 1 sigma and 1 pi bond. I know that my pi bond needs to be formed by a p orbital. I can't have a pi bond formed by like an sp2 or sp3. It needs to be formed by our p orbital, which, when we listed out the 4 atomic orbitals coming off of nitrogen, is right here. So I know that p orbital there is making that pi bond. All we have left now is this lone sp2 right here. So that means that this last lone pair that we see on nitrogen, this only lone pair, is going to be in that sp2 orbital. And now we think, okay, well, can this lone pair move? Well, the fact that it's not in a p orbital, which we need for a conjugated system, the only way electrons and lone pairs can move through a conjugated system is through a p orbital. So because this lone pair is not in a p orbital, it cannot move. It cannot freely travel through this conjugated tunnel, as I was saying before. So I'll say like not in p orbital, and then we could recall that our p orbitals allow for conjugation. I'll abbreviate it too. And electron movement. So that conjugation and electron movement cannot be possible unless our lone pair is in a p orbital. So we kind of deduced from listing out all these 4 atomic orbitals and delegating what lone pair or bond each one is making, whether this lone pair can move or not. So it's kind of that sequential type of step protocol you could do. You can list out all the 4 atomic orbitals, figure out what bonds or lone pairs are being made or within those orbitals, and then from there, if your lone pair is not in a p orbital, you know that thing cannot move around. But in a case where it can move around, that would be our next example, when our lone pair is in a p orbital. So for this, I would say that this is probably going to be the trickiest thing to wrap your head around in this class. Not because it's difficult to understand, but like I was saying before, when we're looking at these molecules like this, we're looking at a snapshot of the molecule in like a single point in time. We're not really looking where these electrons are traveling in any like given moment. We're not seeing the full picture. So because we have this like image, like we snapped a picture of the molecule and this is what we get, we are going to have to kind of use what we know, that what we've established about electron delocalization to understand where this lone pair is going, if it even is at all. So because I'm looking at this snapshot of this molecule, right now I could just find in general where I have p orbitals. So I'll say, okay, I have a p orbital wherever I have a pi bond, flanking each end of the pi bond. So this pi bond here that I'm making blue, I now have a p orbital on my oxygen and my other carbon at the end in order to make that pi bond. Now I could think to myself, well, I have 2 p orbitals next to a lone pair right now, but this carbon here looks suspiciously sp3 hybridized. I have 3 bonds coming off of it in a lone pair, which would be 4 things. But again, remember this is just a snapshot of this molecule specifically. So really, when I see a lone pair directly connected to 2 p orbitals here by that single sigma bond right there, I'm going to highlight that actually. That single bond there, I know that that must mean this lone pair here is going to be pushed energetically into a conjugated system. It's going to see those p orbitals next to it, directly adjacent by that single bond I highlighted, and think, well, I want to join them. I want to be at that lower energy state. So it's going to push itself into that conjugated system, and we'd actually, even though this carbon here with the lone pair looks sp3 hybridized, it is actually going to be, it's actually going to be sp2 hybridized. And it is just the weirdest thing. Like, I remember doing this and I thought it was the craziest thing because I didn't understand like why we could say it was sp2, but that logic you have to go through to see and to understand that these 2 p orbitals are kind of energetically pushing this into the conjugated system is like why we're considering this sp2. And again, in real life, you wouldn't have this snapshot where this carbon looks sp3 hybridized. You kind of have like a smear of electron density, I guess. I don't know if we've done this yet necessarily in this class, but you'd have something that looks like this, where that dotted line is kind of representing like a smear of pi electrons. So you would never have like a explicit lone pair and then a pi bond here. It's gonna kind of, this is the more accurate way to like represent that movement of electrons through the molecule. I can also go ahead and say, okay, we know that carbon's sp2 hybridized. I'm gonna do the same thing I did over here and write like a p orbital here to show that this lone pair is in that p orbital of that sp2 hybridized carbon. I'm gonna draw out one extra little thing really quick as well. I could go like this. We could have something like this as well, without like the wedge and dash and, you know, complicated looking picture. If I just have this molecule in question, this would be another instance where I could think to myself, okay, I'm going to take a step back and just label all my p orbitals. So I have one here, 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 and here. Anywhere where I see a pi bond, I'm going to know that a p orbital is at the end of each of like that pi bond. basically flanking the pi bond at each end. So then I know I have 4 p orbitals in a row right now, and directly adjacent to those p orbitals, I have my lone pair right here. Now, because that lone pair is adjacent to 3 or more of those p orbitals, I know that this thing is going to be able to also enter a p orbital in real life and basically travel through this whole conjugated pathway. So ultimately, that's our goal. We want to make sure that this lone pair, even though in the moment it could look sp3 hybridized, if it's next to all those extra p orbitals, it's going to be energetically inclined to enter that conjugated system in a p orbital, rendering this carbon here sp2 hybridized overall, just like we saw over here. So it's something kind of insane to look out for, but you'll definitely get the hang of it as you do these examples more. And again, this content won't really go away. It's going to totally build on itself throughout the rest of the class. So I know the start to the semester has unfortunately been really rough, but we will continue to go over this. And it sucks because this is like some of my favorite content from this class, but I'm going to go on to the next thing. I'll kind of skip this just because it's kind of like I wrote a subset of conjugation. You really, unfortunately, just have to like memorize what all these mean. It's pretty simple if you think about it. You know if something's aromatic, it's going to be a ring of atoms. It has to be fully conjugated to be aromatic. Like that's kind of a given because we know it's a subset of conjugation. As long as everything's in the plane, everything's flat and aligned, you're good to go. So really it's like it's kind of exactly like conjugation, just worded a bit differently. But the bigger deal here, something that we haven't seen before, was this like 4n+2 thing. Some people in previous semesters had questions on like how to go about this. Let's say like I had a benzene ring here, which would mean I have 6 pi electrons, because we know there's p orbitals on each of these carbons I put dots on. So that would mean what I do is I take 4n+2 and I just set it up equal to those 6 pi electrons I just counted. And then I solve for n. And if n equals an integer, I think in this case it equals 1, then you know that this is aromatic. If the 4n+2 thing worked, like it just did, and let's say the molecule was not cyclic or something, one of these first 3 things weren't satisfied, you'd then say like the molecule's non-aromatic. This is kind of just like know the rules of it and kind of use the rules to kind of come to the conclusion in that sense. So nothing too crazy with this. I'm gonna move on to the next thing because I don't want this video to get too long. But again, you could skip around if anything. This is the new content, all about acids and bases and the 4 tools we can use to understand whether a lone pair is a good conjugate base or not, and what that means for the molecule's reactivity. So we're going to have the atom effect, resonance, conjugation, inductive effect, and our orbital effect. I know these seem like 4 totally unrelated, complicated things, which is why when I took the class, I thought of it as a whole, like, I thought of this as like the umbrella term for everything I listed up here. Yeah, that's what I meant. This is kind of like the umbrella term for everything that we're about to talk about. So the conceptual idea that a stronger acid, so something very willing to lose that H+ proton, that stronger acid that can lose that hydrogen atom can stabilize the resulting lone pair better. So let's say like I'm just going to draw like a random lone pair right now, but let's say I have this lone pair here. And I'm not going to make this like too complicated right now, but if I had this molecule result from something like this. So let's say the first molecule had that hydrogen there. When that hydrogen basically comes off and is floating around somewhere in the solution or on another molecule even, for example, the 2 lone pairs that were in this bond here are now the lone pairs here. Electrons, I mean, not lone pairs. The 2 electrons that were on my left side are now the single lone pair on my right side. So if this is an acid here, the acid is more willing to lose this H plus proton if it can stabilize this red lone pair. I drew it here the best. So anything that can kind of kick off this H and exist as this very unstable, like negative charge, is going to be our best acid, our strongest acid, which by definition is going to be our weak base. The reason I'm saying this, though, is because if we have a weak base, something that can easily lose this H plus proton, that's going to mean we have a stable molecule. So all this like stuff I've been saying is basically me trying to say, if you can have this lone pair negative charge exist and be happy in solution and not need to get this H back to stabilize itself and be neutral, then this negative charge molecule, that version of the molecule, is super stable. So we're going to kind of see this as we go on. And it'll make more sense as I go through some examples. But with the atom effect, for example. So I know, like I said before, if I have a very stable lone pair, I'm going to be a happy molecule. So for the first acid and base atom effect thing, I guess for electronegativity, that first subset that we see up here, I know I wrote a bunch of words on this. I know I write a lot of words in my slides. I kind of use these slides as a basis to go off of in class, and I write on the board. But I really make these kind of wordy just so you could reference them after the class if you would like to. But in a bunch of words here, I basically am going through the logic of that if you have a more electronegative atom, it's going to hug the electrons more. It's going to hug that lone pair more. I like to think of it that way, as that analogy of like hugging. It's going to pull that lone pair super close to itself and keep it stable. So I always have the visual in my mind of like, if I have that same lone pair I drew above, I'm going to draw this a little different here. Again, the distance from the lone pair to the actual molecule doesn't matter. I'm just doing this for analogy's sake. But let's say I had, what do I want to do? I'm going to make this my carbon. I'm going to leave that as my carbon, and this is going to be my nitrogen. So I know that nitrogen is more electronegative than my carbon. I think I said that right. I know my nitrogen is more electronegative than my carbon. So my nitrogen, because it has more of a pull on its surrounding electrons, it's going to kind of hug that electron pair and bring it very close to itself and stabilize it. It's going to keep it very like solid and stable close to the nitrogen atom. On the other hand, on my left side up here, if I have my lone pair on a carbon atom, that's going to be way less electronegative than nitrogen. So this lone pair is going to be way further from my carbon than it was with my nitrogen. So my radius here is going to be like a tad bit bigger. It won't have as good of a hold on that lone pair as my nitrogen does. This was just what helped me when I took the class. I like thinking of it as the nitrogen kind of grabbing a hold of these electrons and kind of pulling them super close and holding onto them tight to stabilize that lone pair. So then overall this would be our more stable lone pair because of the fact that nitrogen is pulling the lone pair even closer to itself. So that's how I like to think about that. And kind of in a similar sense, we have radius for atom effect now. This, while my last slide kind of dealt with the hold we have on the electrons, I'm going to write that as well. So this had like a tighter hold on the electrons. This now is going to deal with how spacious our electrons are in our atom. And this has to do with going down a row. So up here, it's always across a column, across a row, and this is always down a column. So I always in class kind of represent this as a bunch of electrons scattered in my atomic radius. I'll do 3 for now. and I'll do the 3 here. So you can kind of think to yourself, you know that electrons want to repel. So are they going to be happier when they're super packed tight like this, or when they're more spaciously distributed here? And the answer would be, well, if my electrons are repelling, they're not going to want to be close to each other like they are here. And on the other hand, they're going to like being very spaciously distributed down here in my iodine or bromine, for example. The fact that they can spread out more because of those new atomic radii we're adding onto as we go down the column, that's going to make for a much happier electron pair or electrons in general in our molecule. So if I did have my, I'm going to actually do this a little different. If I did have my fluorine, for example, versus my iodine, I'll go on like opposite ends of the spectrum here. I could draw my radius around fluorine as like a tight circle. My electrons are super packed and super condensed to this fluorine. It's going to be a very unstable atom. On the contrary, though, I'll make these negative as well, since I am talking about atoms with lone pairs. So on the contrary, though, if I do have my iodine in its negative formal charge version of itself, this electron pair around itself, or all these electrons around it, are going to be in a much larger atomic radius. So now all these lone pairs and this negative charge can spread out more efficiently and be more comfortable, is how I like to think of it. This is going to be a much happier molecule here, or atom here. So when I am thinking about these two things, for electronegativity, I think of my hold on the molecule. I have a better hold on my lone pair in my molecule as I get more electronegative. And on the same idea, I have a more spacious and comfortable arrangement of those electrons as I go down my column. So if you did have the whole periodic table, the most stable molecules would be anything to the right and down below. So really, iodine would be like our most stable lone pair we could possibly have, because it's at that bottom right of our periodic table. Again, I kind of just wrote all this here to kind of go through the logic of why this stuff is the way it is. But again, it just has to do with electronegativity above and atomic radius here. Those are the two fundamental ideas that deal with like why a lone pair may be stable or not. So then kind of similar, we already kind of talked about resonance, so I'll go over this like super quickly. But if our p orbitals are adjacent and aligned and we have 3 or more, that, like I said before, is going to lower the energy of our molecule. So our lone pair in that p orbital conjugated system is going to be able to kind of smear itself through that tunnel of p orbitals and stabilize itself way better than if resonance wasn't there. This is kind of, I don't want to say self-explanatory, but kind of stuff we've already hinted at before. So I'm going to kind of skip over this a little bit really quick. So the larger the conjugated system, ultimately the better stable p orbital or lone pair you have in that p orbital. For inductive effect, this has nothing to do with the actual movement of electrons. We're not explicitly shifting them like we see in resonance and conjugation. With resonance and conjugation, you see pi bonds flipping around, or you see lone pairs becoming pi bonds. You're basically explicitly shifting those electrons around. But here, there's no shifting. I think of this as those diagrams that you've probably seen of like electron density, where you have the more red regions and the more blue regions kind of signifying where there's more electrons localized. I think of that with this as well. I think of that kind of like red and blue like density map that I'm sure, I hope you guys have an idea what I'm talking about, but there's no actual shifting here. We're not going to have any arrows or anything. It's just the concept of our electrons, our electronegative atoms here, or electronegative chlorines here. I'll use this example first. They're going to be able to pull the density of electrons from my oxygen through these sigma bonds here. And what I recommend doing for things like this is whenever you're thinking of acids and bases and trying to determine which one is more acidic, more basic, which one's just more stable overall, the best thing you could do for yourself is to pretend that H is not even there anymore. Pretend the H plus completely came off and you're left with just a simple lone pair. So I have the two that were originally there and then the one I just made when I took that H off. So now I could think, well, if I'm considering this lone pair here, I'm going to make this one red actually to show it's the one that we just made to bring on this negative formal charge on our O. I'm going to think of this as, now I know I have my two super electronegative chlorines nearby. These are going to pull my density from my O, all that concentrated like negative electron density, through these sigma bonds here that I'm highlighting toward the Cl. And ultimately, if you kind of imagine that pulling through these sigma bonds I highlighted toward those chlorines, I kind of envision this lone pair here kind of going closer and closer to the oxygen, and kind of like the oxygen, like I said before, hugging that lone pair. It's keeping it super stable and super close and making it more comfortable overall. So that idea there is really going to make our molecule, in this case here, a way better acid and a very weak base, which is what we want. Our weak bases are going to be our most stable bases. They're not going to need that extra H plus added on or added back on to stabilize themselves. They're super happy and comfortable being in their negatively charged form. So the last thing, orbital effect, this is much more simple. If any of the other tools we've talked about, the atom effect, resonance conjugation, or inductive effect, if those are not coming into play for determining your stability of your molecule in your lone pair, then you go back to this idea. And ultimately, anything with the most S character is going to be the most stable conjugate base and therefore the most strong acid. So I kind of always think of just this diagram up here. I know I put all this down here, but really, your lower energy if you're SP, and then of course it just keeps getting higher. So in this case, we have our SP hybridized molecule with this lone pair in an SP hybridized orbital. That's ultimately going to be our most strong acid and our most stable conjugate base compared to something like this, where we have a pK of 50. We're not going to be a great acid here. And it's just because this lone pair is in a much less stable orbital. This is the main thing I wanted to get to, honestly. So, with Newman projections, I know, unfortunately, I'm not in person to talk about this, but whenever we're talking about alkanes, kind of shifting to that right now, sometimes seeing them from a different perspective can be extremely helpful. And the way we do that is with Newman projections. I know we've had a lot of practice with this so far on her like LEAP assignments and ALEKS and stuff, but the way I have done this in the past, or the way I've been told works best for people throughout all of the years I've like done this. And also, I know I'm talking super fast right now. I'm so sorry. I just don't want this to be like a super long video for you guys. So, but anyway, the two things that I can do, or I usually do, or you know, you don't have to do both of these. It depends on what works best for you. I always imagine myself reaching out into my screen and grabbing the bond between the two carbons I'm looking down. So in this case, carbons X and Z. I'm gonna like pretend I'm doing this with my right hand in this moment. I know I'm not, you guys can't see me, but like you could probably envision or go along with it. I envision grabbing this bond here, and then depending on which way I'm looking down this bond, in this case I'm looking down from X to Z. You could also look down from Z to X, which I'll talk about in a second. But let's say we're looking down X to Z. I know that my front carbon should be this X, and my back carbon facing away from me should be this Z here. So when I do reach out and grab this bond, I'm going to imagine turning the X carbon so it's facing my eyes, and so that the Z carbon is facing away from me on the opposite side. So it's like the furthest one toward me. So if I grab this here with my hand, turn the X facing toward me so it's literally like right in front of my eyes, the first thing I see, I can then kind of envision where all my substituents are around these two carbons in the center here, X and Z, and draw it as a Newman projection. So when I grabbed the bond between X and Z and turned it toward me, I now know that this group here is going to be facing straight up. It's in the plane, going straight up, so I'm going to put that here. On the other hand, on the bottom, my wedge and dash. This can kind of get a little confusing if you're, still getting used to envisioning things 3D. But I know right now that in this plane of the page, just this image we have here, if my OH is facing toward me, it's wedged, right? It's coming out of in this case, my iPad right now, or the board, or whatever you drew your molecule on. It's coming out at us, while the CH3 in the back here is going down below the paper or your iPad or the board you drew this molecule on. So when I grab this and I turn X toward me, so it's face on with my eyes, I know that the OH is going to go from coming out toward me to moving toward my right. And it helps to kind of, sometimes I take my pencil and I kind of hold it out of my iPad, and then as I turn the X carbon so it's facing toward me, I just shift my pen or whatever I'm holding in that same direction, and you'll see that the OH kind of falls to the right side. Same thing with the CH3. I sometimes put my pen like below the table or behind my iPad, and when I shift this whole molecule, I grab the bond between X and Z and turn X toward my face. That CH3 that I'm holding below my iPad is now going to be on my left side of the page or whatever I'm writing on. So I'll be right here. And same thing with the back carbon. The deuterium and H are going to kind of overlay so that one is on the right and one is on the left. And same thing with the bromine. We know that's in the plane, so I'm just going to draw that straight down right here. If this kind of is a little confusing for you with those wedges and dashes, the next thing you could do is, and I know it's hard to do this when you can't see me in person, but I'm going to take my right hand right now, and I'm going to designate my thumb as the deuterium and my pinky as the hydrogen. So I'm holding my right hand out, my thumb is deuterium, my pinky is hydrogen, and I'm going to turn my palm so it's facing upward. My palm right now, we could say my palm is X, and then the back of my hand is the carbon Z. So as I turn my hand so my palm is facing me, carbon X is what I'm looking down. I'm looking down my palm in my face right now. You'll see that your thumb ends up on the right, and your pinky ends up on your left. So that can also be something super helpful that you can do too. If we were looking down the other way, for example, you can use your left hand and say, okay, deuterium is your thumb, hydrogen is your pinky, and then turn it so the carbon Z is coming at your face. It's like your palm directly toward your eyes right now. You'd see that the deuterium is now on the left and the hydrogen is on the right. So the perspective switch, and the reason I'm saying this is I have it a little better visualized on these two slides. I made this a few semesters ago because I thought it might be helpful to really see what's going on when we're trying to visualize these things as 3D. So what we did before up here, the original example that I actually have like physically written down, we were looking at it from the left to the right, so X to Z. You'll notice that we had our dashes on the left here and our wedges on the right, just by the perspective we happen to be looking down. But if we flipped to look down this from right to left, from Z to X, from Z to X, now you kind of see that, I'm going to keep going back and forth. The dash flipped to this side, and the wedge now flipped to this side. Nothing about the molecule changed at all. This is still the exact same molecule I had above, but because we're switching perspectives, our diagram, our Newman projection is naturally going to kind of flip too. Upward and downward are still obviously the same. You can't really change that unless you like flip the molecule over, but when you look from left to right or right to left, that's just going to change the left and right and left sides. If you can't visualize things 3D, or you feel like you might like trip yourself up a bit, because I know this is definitely like a new thing we're doing in class. If you draw this diagram out, depending on what side you're looking at, you can then kind of fill in the substituents on either side. So like, for example, right now, If I'm looking at carbon Z, I know that carbon Z here is my front carbon. So I'm going to just label that there really quick. So if I see my deuterium here, I'm going to draw this as kind of like, I'm going to break this up a little bit how it did on the right side. So my horizontal line, I'm going to go kind of cut through the molecule like that. So now we have our up and down sides of our molecule, kind of splitting this up horizontally. And now I'm going to envision where this deuterium is. So I know it's up above this XZ bond. Just when I extended that out, you can kind of see that. It's above this bond, but it is also wedged. So I know up wedged would be right here. And you can fill that in right there. And same thing in the back. The hydrogen is up dashed. That would be right here. And same thing, bromine is down in the plane. Down in the plane would be right along this line here. It's not on either side. It's just right perfectly in the plane, in the plane of our page. And same thing with the back. I'll just finish this really quick. We have carbon X back here, our giant circle in the back of our Newman projection. That ethyl is going to be up in the plane. So I'm going to put that here. Same thing, this OH is going to be down wedged. So that would be right here. And then our CH3 in the back is going to be down dashed. That perfectly lines up with this here. So I'm going to write that in there. So these are super helpful things you can do with Newman projections, whether it be visualizing it like this or fully identifying whether you're viewing from left to right or right to left and then drawing this diagram out. Whatever works for you, even if it's a combination of both, you'll be able to kind of see how we're shifting our perspective to look down this molecule differently than the actual picture or image we're given. So this is a super helpful tool, like Newman projections in general. So hopefully some of this might help you. But again, in class, it's so much easier to explain this, and then I could actually answer your questions in the moment too. So I know this is kind of unfortunate, but I thought I'd do this anyway just in case. And last slide. So with chair conformations, drawing these is insane. I'm going to be totally honest. Like, you have to kind of get the hang of, like, okay, you're going to have two slants like this, and then imagine, like, a little triangle on each end, and it's not fun. So what I do, you might see me doing right now, I'm putting dotted lines in there. Those dotted lines helped me so much when I was taking this class, because it allowed me to see the actual folds and bends in my chair conformation. Instead of just looking like a random like squiggle of lines, it kind of helped me see 3D a little bit. So like here, for example, we have the triangle kind of facing up here. We have this little rectangle or square kind of also angled up this way. And then now facing down, we have another little triangle. So you can kind of see that like zigzag kind of nature of this in 3D. I always think of like taking a piece of paper and folding it in threes and making it so that one, like either edge of the paper is pointing opposite directions. So let's say like each end is like one is up, one is down. And then that middle piece is kind of like angled as well. I just imagine kind of folding a piece of paper up so it has that like zigzag nature to it. So that's really what we're doing here. But yeah, those dotted lines helped me so much when I took this class. So hopefully looking at this kind of makes more sense to you than just like compared to just looking at something like that, because this can definitely be confusing. Like even right now, it's insane to kind of draw these out like that. Sometimes just doesn't do it for me. So envisioning that 3D like dotted line aspect can be helpful. But the main thing I want to say about this is when we're flipping between chair conformations, you're never going to change whether something is facing down or whether something is facing up. This here, this image I put on the left, that molecule, this is as if we were looking at a cyclohexane from above. And I'm sure Axelson has obviously said this before, but just to repeat, we're basically looking at this thing from above. So naturally, the dashes are going down below our page, and the wedges are coming up toward us at our face. So when we kind of turn this thing on the side, if I was in person, I'd like kind of turn my, like the whiteboard, the tiny whiteboard, or my iPad to the side. If I was looking straight down through the edge of the iPad or little whiteboard or something, I'd see these here, my chair conformations. So again, this is just a matter of perspective. Going from here to here, we are not changing anything at all. All of our connections are the same, the molecule is identical. We're just changing the way we're looking at it. But between chair conformations, again, we're not changing the molecule itself. We're just changing the way each of these flaps is bent. So you might see this like left triangle here. It's kind of pointing up right now, right? But on the other side, on the right side, it's kind of pointing down. We're basically manipulating and like flipping the directions those little flaps of our chair are pointing. So everything's staying the same. Nothing about the molecule is changing. We're just changing whether things are axial or equatorial. Nothing is changing about being down or up. You might notice for this carbon 1 here, I'm down equatorial here, then I switch to down axial. So my direction is not facing just the axial and equatorial nature of these things. Same thing with carbon 2. I'm down axial here, I'm pointing straight down. But now, over here, I'm down equatorial. So I'm still pointing down. And something I do in class too is I also do like a little horizontal dotted line like this on my carbons in question. You can kind of see that right now, if this is like up and down below that horizontal line, I'm down here pointing straight down. And I'm still down here despite being on that slight angle. That slight angle, instead of pointing straight down, just signifies that I'm equatorial. Same thing here. I'm up equatorial here, if you envision that dotted line. I'm above that dotted line. I'm above that horizontal. But then on the other side, I'm still up here, but now I'm axial. I'm pointing straight directly up. Same thing again, up equatorial and up axial. So up and up stay the same, down and down stay the same. You're just going from equatorial to axial, vice versa. Another thing with this that can sometimes be a little confusing to envision is how do you know like whether to put something down axial, down equatorial, up equatorial? Like how do you know whether it's axial or equatorial in itself? So to do that, I go in and I'm gonna highlight one of these. I'll start with carbon 1. I'm gonna highlight this set of bonds right here. Just that shape here. And I'm actually gonna go a step further and draw one imaginary bond going up too. I mean, technically we do have an implied hydrogen there, so I will draw that in. And I'll draw it in over here too. So right now, I'm gonna copy that same highlight on the opposite side, but you might notice something changes about it. So they kind of look like the same shape, but notice how they're kind of upside down in relation to each other. So all this is our tetrahedral shape. So when we have like a tetrahedron in 3D, you kind of have that like chicken foot shape. It could also be upside down like I did on the right-hand side over here. It kind of looks like a foot of a chicken or something. And this is the shape we're going for when we're drawing these conformations and their substituents, axial or equatorial. So you kind of see like this overlays here. This shape, that upside down foot shape overlays perfectly here. The idea with this is that we just want the angles between all these bonds to be nice and like 109.5 to make sure that we're stable. No, it's nothing different than that. I know drawing them can get a little weird, so what I usually do, in addition to this idea that we want that tetrahedral shape, is I envision kind of like a zigzag going on in my chair structure. So like, I'm going to use a highlight for this actually. So I'm going to start between carbons 2 and 3 on this side and keep going. So I go from 2 to 3, I'm like up there. I kind of have like an up slant. I'm drawing my line up, and then I draw my line to 4, kind of down, and then I go up again, and I'm just going to keep following this zigzag arbitrarily. So I'm going to go up here, down again. I'm just going to keep going like that. So you could kind of see that like zigzag shape going on here. So when I'm drawing in my substituents, I know that it should follow that shape. So for example, like if I needed to put something up equatorial on carbon 2 over here, I know that, well, I have to follow the zigzag for it to be equatorial, kind of slanted off to the side, not pointing straight up or down. So I'm going to put that right here following the zigzag. Let's say like I just put a BR or something on this. And same thing on, let's say like the top. I'm going to be following that zigzag I see here. And you don't have to keep going. Like I could have easily just stopped right here. I just kept going so you could see the actual like zigzag formation. But let's say I wanted to put something up here, up axial. Then in this case, I can't necessarily go down this way because my equatorial is facing the down direction. I'm kind of at that like downward angle here. If I imagine my horizontal here, I'm going below that. So instead, if I do want to put something up here, I'm going to need to follow that kind of like chicken foot shape again. So again, I have all of my bonds here, like the actual feet going on. And then put the implied hydrogen here. That was already there, I just drew it in. So now if I want to add my fourth thing, the only spot it could be then is my up equatorial area. I'll just do BR again, just to distinguish it from everything else. So you can kind of see that shape being followed here. Same thing on like carbon 4. If I wanted to add in a fourth thing, and let's say I wanted it to be facing down, it's gonna naturally have to be facing down because I have, again, that like chicken foot shape. My like beam coming out of those three little like tripod shape thing I have going on here, the only like support I have for that is this direction, straight down. And then I match this shape here. You could think of that too as like a tripod, I guess. Anything that like makes sense to your brain, absolutely go for it. But it always follows that tetrahedral shape there. So our next thing I'd put here, let's say like Axel Sen said, like add a down axial group, you'd know it would have to be going straight down this way. I'll just make it an H or something. But it's always going to follow that red chicken foot tripod shape that I drew in. And to help you with the axial and equatorial direction, you can always just continue the zigzag like I did in blue highlight, and hopefully that would kind of give you like a clear picture of where all these things map out. But again, when you actually are doing the chair flip, nothing will ever change down or up. It's only going to change whether it's equatorial or axial. But yeah, I know this is not the best recorded. This would be so much easier in person because it is by nature a very visual thing. But hopefully maybe this clarified some stuff for you a little bit. Even if it didn't, I still wanted to record this. I just felt like it was the best thing to do. So I'm going to send out my office hours soon, and I'll answer your guys' questions. You could email me also, but yeah, I'll see you guys next week.